Hi. Okay, so let's go through just these two simple questions that basically involve the latest topics that we have learned. The latest topics we learned, if you recall, is the reactivity topic, which is kind of covered by question 5 here, and periodic table, which is kind of covered by question number the long question, the question number 8. And also question number 8 is a database question. So it's a bit tough, but I just want to let you have an experience of what these kind of questions will be. Okay, so before you start, you should try the questions. Don't worry about it. You try first, then you watch this video. Okay, let's look at question 5. Oh, so it seems like there's a reactivity series here. So good thing is that you don't have to remember the series. You have to remember the series. But in this case, they give you a modified version. So if they give you, we use it. But usually you don't, right? So if you recall, P, S, C, please stop calling me a cute zombie. I Yep. So you need to know this series, and the idea of displacement. Alright, so let's take a look here. So they say which metals. So before I do anything, I see the word, there's a S here. So this is more than one. Right? So it says do not react with acid. So what happens here? So if you recall a metal, so you choose any one of this metal, let's say Mg lah, Mg plus an acid. Well, you can choose nitric acid, you can even choose HCl, any acid. Okay, so A, you notice this is an element. Recall I mentioned, if there is an element has a reactant, it's a very good chance that it might be displacement. So we check. So in this case, you have magnesium versus the H. Oh, magnesium higher wall. So magnesium will kick out the H. So H is kicked out as H2, and you take its place. So please do not commit this error here. This error is to do with formula. Okay, let me zoom in. Formula of ionic compound. This is something that most of you will commit lah, but don't waste, really don't waste. Do intentionally be careful. What do I mean? So now you need to think about a formula between of ionic compound that has Mg and Cl. Means your natural first reaction, 1 Mg 1 Cl lah. Please no, please check the charge and balance accordingly. So Mg is actually a 2 plus, Cl is a minus. You do your cross method, you end up, oh, it's MgCl2. Just an extra few seconds of doing this step and you save the mark. You actually get that 1 mark. So MgCl2, and I'll quickly balance it. So from this reaction, this acid metal reaction, it seems like I kind of need to kick out the H. And recall, to kick out the H in to be more reactive one. So look at the series that's given here. Which metals here are so-called more reactive than H, which means they can kick out the H. So if you realize, these 4 metals are above H, means these metals can react with acid. They can kick out the H and replace it. So the metals in red, no go. They are less reactive. They cannot displace it. They cannot react lah. So the answer here is copper and Hg. Yep. Okay, part 2. You are supposed to describe an experiment that will confirm what we have just predicted. Oh, very simple. Then you will add copper and Hg separately, of course, separately, to HCl solution. So you see, it produces a gas. So if it react, I will see bubble. So it doesn't react. So you say that no effervescence observed. Yep. And when it has no effervescence observed, it means your prediction is true, and it is true lah. So in WA3, I think we accepted bubbles, but we are not going to accept bubbles from now on. Please write down the term effervescence and learn to spell it. It's pretty useful, alright? Okay, next. State a metal whose hydroxide do not decompose. So don't panic. I think you see, hydroxide can decompose, man. So now let's trigger some knowledge. So if you recall, that 7 reactions we learned, one of the reaction is metal carbonate becomes metal oxide plus CO2. You recall. And you also recall, so what do you need to know? You need to be able to write this equation and know the trend. So the trend is the more reactive the metal, the harder it is for the metal carbonate to decompose. So much so the top 2 metal carbonate will never be composed. Never. Potassium and sodium. Their oxides will never be undergo they will never decompose. So this is what we learn for carbonate. So in this question, I see some similar words. The words I see here is decompose and hydroxide. Decompose. It's not a carbonate, I know, but you see carbonate is CO3 2 minus, hydroxide is OH minus. These are all like complicated anions. So I guess is to you will look at it and go like, I think they are quite similar lah, and they are. So they should behave in a similar pattern. So what do these 2 metals have in common? They are both group 1 carbonate. So is there a group 1 carbonate in this question? A group 1 here. Have. Answer is rubidium. Rubidium is your group 1 metal. So it should follow the trend of the potassium carbonate, sodium carbonate. Another way to look at it is, if you recall, down group 1, the metal get more reactive. Your rubidium is below sodium and potassium. It's more reactive than both of them. So it will not decompose. Part 4 don't need to do, don't worry, we don't learn oxidizing agent yet. And the last one, part 5. Which metal in the series can form a negative ion that, so what is this? Oh, sorry, this one don't need to, we don't really learn this now. Yep, so this part 1, part 2, part 3 is basically related to the reactivity, alright? Okay, now let's go on to this question. I know it's scary, it's very long, so I guess it's kind of like comprehension. So usually you will look through the passage briefly to get an idea. Then after that you look at the question and find that specific segment that help us to answer. So, describe the relationship between the atomic radii and electronic configuration. So see, I'm focusing on few words here. Describe relationship. You do not have to explain. Describe, it's like, this one increase, this one decrease, something like that. Alright, so keyword here, atomic radii or an electronic configuration. You take a look. Atomic radii and electronic. So it's here lah, ne? So what can we see? Oh, it go from 281 to 282 to 283 to 284. Okay, so the valence electron is increasing, if you realize, right? Or the electronic configuration is increasing. And what happened to the atomic radii? Drop one. So how do you get the mark? You just tell me that atomic radii, let me change color. So the atomic radii decrease, right? 186 to 99 when your electronic configuration. Increase. Right, you can see, right, it goes from 281 to 282 to so on and so forth. That's all. Because it's a describe, right? You just describe, oh. Okay, next one. Again, describe. But now you say, what's a trend? Describe the trend of your ionic radii. Okay, so let's focus on the atomic radii. Let me highlight it, alright? Ionic radii. So let's see. Oh, I see the word ionic radius here. And from our eyes, we can see that there are two trends. Or rather, two group of data. And we will describe them. So I will say that ionic radii decreases from Na plus to Al3 plus. Yeah, that's what you can see, right? So it is your 0.95 to 0.065 to 0.05. But you see the other set of data, very different values. So we also tell them, so the ionic radius decreases from P3 minus to Cr minus. Oh, that's it. It's describing what we see, you see. So actually, it's not that tough. It's just, oh, I'm supposed to read what is given, pick out the relevant data, and just write it out. Next, also describe. But in this case, let's choose a different color, orange. So it's about how ionic radii is different from atomic radii. Okay, so let's take a look then. So, atomic versus ionic. Okay, so we can see a pattern here, you see. Pattern, this is the first pattern. And second pattern is here. So first pattern we can see here is the orange. Your cat eye. So I go from sodium to magnesium. So go sodium to magnesium to aluminum. These are all metals. Then look at their cation. We can see that the cation is smaller than the atom. So tell them the radii of positive ion is much smaller than atomic radii. Again, let's take a look again. 0.186, 0.095, 0.16, 0.065, 0.143, 0.05. So the ionic radii is significantly smaller. Then now let's look at the red color. 0.11 to 0.2. Wow. 0.1 to 0.184. So it seems like there is an opposite trend. Okay, write it out for them. So the radii of negative ion is much greater than atomic radii. And how do you know this? I look at the data and I just see a pattern. That's all. Next. So you have two students making two comments here, and you are supposed to explain each comment whether it's supported by the information. First, they say ionic radii linked to charge. So what can we see here then? It can, eh? So say again, I repeat. Ionic radii linked to the charge. So let's look at this group. The charge increase, +1 to +2 to +3. And the size go from 0.095 to 0.065 to 0.05. Oh, it seems like my charge go up. Or rather, sorry, my positive charge go up. my ionic radii dropping and tell them no. So it seems like there is a trend, which means is student 1 correct? It is correct. So you say student 1 is correct. It is supported because why? For cations, okay, I am writing cations. Can you explain using the data for anion? You can, no issue. I'm just writing for cations. So for cations, when the positive charge of ion increase, we realize that ionic radii will decrease. Just now we saw it already, right? Yep. And apparently what you need to say, explain your reasoning. I will even quote the data for them if need be. So for example, okay, don't need example, you just write. So your Mg2 plus has a greater, so you're supporting with an actual example, greater charge than Na plus. But Mg2 plus also has a smaller ionic radii than Na plus, and that will give you 2 marks for statement 1. What about statement 2? They say ionic radius and electronic configuration. Then let's take a look. Ionic radius is weird then the one that has 2 segment, and electronic configuration, that it doesn't seem that it fully commented. What am I talking about? Okay, let's see. So you're looking at, I'm going to use a red pen, a green pen. So you're looking at these 2 segments. All the ions here, Na plus to Cl minus, they have different electronic configuration. So like you can see there are 2 groups, 28 and 288. So let's say I focus on 288 this. So the 3 of them, P3 minus, S2 minus, Cl minus, they have the same electronic configuration. If it is indeed linked, shouldn't they have the same ionic radius? No, right, correct. In this case, the ionic radius changed. So that is the answer. So what should I write? Student 2 is wrong. So for example, for anions, again, you want to use cations data, it is also not wrong. So for anions, the number of electron in each shell, each electron shell is the same. For example, the example is now 288, same, but the ionic radii changes. Quote the data. So for example, P3 minus, S2 minus, Cl minus, they have your 288, but your ionic radii changes. There's change. There's a change. That's it. Next one. Oh, suggest why it's not possible to use. Oh, so you are talking about what here? You're talking about measuring an atom. Argon. Okay, let's see the question. Oh, look at here. Measure atom. So let's see what they are trying to say. They say, oh, possible to measure the distance between the nucleus or nuclei of 2 atoms. Okay. But argon got 2 atoms meh? No, right? Then how you measure? So that's the answer. So tell them, argon has a full electron has full electron shells. Which means what? Which means it do not have to gain, lose, share electron, and bond. Meaning it will exist, has alone by itself has atoms. So there's no molecules. How do you even measure? You can't measure what. And lastly, why is there no ionic radii for silicon? So we have Na plus, Mg2 plus, Al3 plus, P3 minus, S2 minus, Cl minus, Si leh. So why? What's the reasoning? Oh, because for Si, okay, for Na is easy because why? You have one electron, one valence electron. Either you gain 7 or lose 1. You then just lose 1 easy ma. There's an easier way out. But silicon leh? Silicon got 4 valence. You either gain 4 or lose 4, which is difficult. So you rather just share. So we write down, that's what the answer is. Silicon share electrons. Therefore, it does not form ion because it share ions. If you form ion, it doesn't form ion, what ionic radii are you talking about, right? Yeah, so that's about it. Thank you.